Does it work? Or it kind of works. Can you hear me? I think so, right? All right. All right, today's the office hour for the kernel exploitation or the QQ. So if you have any questions, just ask me. Technically speaking, the office hour hasn't started yet, but it's my first time streaming, so I just wanted to have half an hour earlier to do some preparation. But apparently the setup works. So yeah, if now have any questions, just ask. We will do it until I think 5:30. And maybe start recording. So the scoreboard is still like before. NY32 is on top, solved 5 challenges, and now we have a few other solves. And then, well, for KBFS, the QQ, there is only 2 solves, both from Zolto. Well, apparently Zolto just got PC control for level 3 for the QQ. It hasn't already officially started, but feel free to ask any questions. Yep. Yep. So yeah, let's. If you have any questions, just shoot it. I can answer them, and I will answer questions both for the kernel exploitation module and also the new kernel exploitation module and the quarterly quiz. Yeah, I would definitely recommend using GDB for debugging. So what I would do actually is to get the a location of the kernel module, and then set breakpoint at the allocation sites, and then read out of the allocation object's address, and then inspect the memory inside GDB. Let's say oh god, I need to start, let's say, level 1. Oops. It's quite slow recently. We probably need practice. Sure. Let's make it even larger. Oof, no, not this large. Does this work? Okay, cool. And then this is practice. Okay, VM connect. Now we have VM debug. Now we continue. VM connect. Oof. So, do we have sudo? Yeah, we have sudo. So, what I will do is that we first go to grab, I think it's called challenge, chaos sim. So we can get the location of the modules. Sorry, the module functions, and then we can see it inside GDB. That's a lot. And we have copy from user. Copy from user. We actually don't care about copy from user. We care about this allocation site. We actually don't care about the allocation function, allocation call. We actually want to know its return value, which is what's get returned by the this is the object that is returned by the kernel module. We set breakpoint here, and then we talk to it. How do we talk to it? Oh. Let's do this. You won't be able to see things. Should be fine. Oof. We shouldn't be. Okay. We shouldn't be compiling inside it. K-mem cache alloc will return a memory location of where the kernel allocation memory to like malloc. That's correct. But then in this level, in level 1, we have k-mem cache alloc. In later levels, we are going to have k-malloc, which is a different mechanism, but same thing. It will return a pointer to the memory region, just like malloc. Let's see, XP solution level 1. Okay, and then we run it here. We'll hit the breakpoint, and then it will return in RAX. So this is the location. This is how we see what's being allocated. And then if you read the blog, I think, no, the slides about slab allocator, I think you will say that the allocator using Linux kernel is slab, and then it has a free list in each slab. Wait, what? Not here. Here, 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 here. No. All right. Well, it's I think it's not covered by Robert yet. So I'm going to explain how kernel heap works. Here, this is the object, the pointer that is returned by mem cache alloc. It points to a memory region of size actually 0x200. It's actually this, if I remember correctly. And then you will see a pointer here. This is another kernel pointer pointing to the next allocation site, just like tcache in the user space. Maybe we should just write a small thing here. How do we interact with it in the first place? Actually, let me copy it out. One PLC, C, let's do this. All right. So I'll demonstrate how it actually works in memory for level 1, I guess. So let's go to cd test make up on college, and then cp on college challenge. Is it like this? Okay. So we can see that the most important functions here are actually kheap iocto, and then you will do some location if you path. God, do X. Let's do this. So if you read the decompilation of the kernel, oh, I need to. I'm trying to turn to make the font larger. Is it good? Or maybe 60? So when we're investigating a kernel module, so the first thing we need to do is to look at the init function. So if we read the disassembly of the init of the kernel module, the first thing we'll realize is that it will actually open up the flag file. Field open is the open function inside the kernel, how the kernel opens a file for user space. So it's actually a field p. Field p. And then you will read, at most, you will read from it this thing into so you will read the flag into this flag buffer, and then close the file handler, of course, and then create a kmem cache. We don't actually need to care about the flags here. It's just fine, and then it will create proc virtual device called kheap. So what we want to do is that if we want to learn how to interact with this device, okay, I'm going to. We can find it inside. Wait, this is the host. Oof. I hate ASU's firewall thing. Connection gets killed. Come on. All right. Yeah, the point is, the kernel. Oh my God! Come on. Box, I think. Seeing. What? Oh, you're totally right, Connor. So as we can see here, it will create a proc file inside the proc, and then it should be called kheap. Does it have this thing? Apparently it is. So this is the thing we need to interact with to exploit the kernel. Actually, in the level 1, it's more like a playing type of situation, so we actually don't need to pawn the kernel, as we can see here, because there is a buffer inside memory that contains the flag. We only need to read it out. But how? Probably use some vulnerability. So here I'm going to write it. I'm going to write a thing from start that to interact with it. So first thing first, we need to open up the proc kheap thing with read write primitive. We probably need a file control here, and also unistd, I guess. Unistd. Okay. And then now we look at what's going on with this proc entry. So when we do it, we only need to. So this thing specifies the. This thing, I think it's O. So this thing is actually the permission of this file, the proc entry. So actually, don't need to care about this. The only thing we need to care about is what kind of operations, what kind of file operations is associated with this thing. All right, and we double click into it. It turns out there are only 3 functions associated with this proc entry. What does it do in open? So it will allocate a object. So what it does is actually will locate a thing. Let's don't do it. Let's do this. All right. So apparently, so examine that structure. Yeah, I mean, examining that structure is how you figure out how many file options there, and then the way you do it is like this. Then you can see, oh, you will print out device open and stuff, which doesn't matter. If you want to look at the size of the cache P, you just double click it and see where it is defined. It's actually in init, right? It says the size of the thing is actually here. This is the size of this object when you create dedicated cache. Well, in later levels, there will be kmalloc, which is even easier for you. That the size is just an argument to kmalloc. But here we know that size is this. Okay. Now we continue investigating the thing. Where it is? Open. All right. This is object. Cool. And then if the allocation fails, you will just return fail, which is bad for us. If the allocation success, well, apparently this is a bug. But anyway, if the allocation success, it will assign a function pointer to the thing, and then clear out the other side of it. So we clearly know that the size of the thing is well, let's just call it object T, and then we know that there's this thing, and 1 2 3 4 5. Well, let's do this. Char A equals 1 T 0. I think so. Let's do it. Let's see. And then we type this object T star. Alright, this is some pointer. Boom. Now we know that you will create object. So when we open a K heap entry, it will first thing is it will locate this object and then assign a function pointer that will do a print thing to it, and then clear out the rest of the object, which means that there is no use of initialized value possible in this object. That's just open. So next thing we will see is release. Apparently it will just free the thing, and that will be it. All right, but so next thing will be iocto. What does it do? Oh my god, this is complicated. It's okay. So the thing we'll do is to, if you want to turn the thing, it's this weird thing, into legible text, you just press A. That would be it. You just press A. Can he? And then private data. So as we saw before, private data is the object. So object, and then with property type it. It's object T star. Okay, now we see the thing. This is a function pointer, and the field is, let's call it data, because we don't know what that is, or call it buffer because we don't know what it is yet. All right. So if the command is this thing, it will invoke the function pointer, which is good. Which means if we can somehow override the function pointer, we can get piece of control. The first thing is we need to interact with it. We can pass an arc, uarg, I'll call it uarg, uarg to it, and our arguments will be passed into kernel request, and then yeah, this is complicated. If the command is this, you will allocate another thing. This is because it's from cache P, so it's the same object, so it must be object of type object T. So you will copy the flag into this buffer. That means by invoking this command, we're going to allocate a lot of flag objects in the memory, and we'll be able to see it because we have debugging capability, right? We'll be able to see it in memory. This is the flag of J, but let's try checking other stuff as well. Copy to user. So copy to user takes 3 arguments. Okay. And wait. That looks very wrong, right? Did you realize that you will only report a bug if the size is larger than this thing. But then our object has maximum size of 0x1d8, if I remember correctly. That means that's a clear out-of-bound read. So now the exploitation plan is quite clear. We allocate a ton of the flag objects, and we use the OOB read primitive and read out the flag, and that will be it. But let's see what else. So size copy from user. This means this command will take user input and without any bound and write to the object buffer. But then, as we know before, as we learned, object buffer has a size of this number of bytes, which means it's a clear out-of-bound read-write primitive. And now what we can do is to allocate a ton of flag objects, and then out-of-bound read-write, and then that will be it. Let's do it. How do we do it? Oh, let's send it to background. Oof, I hate ASU. I hate ASU's network setup, because we can define the size in a request. That's correct, and there is no check on the size. That's why it's an OOB vulnerability. XP, C. Okay, now we need to do. So usually when you write exploits, you want to write functions that do one thing at a time. So remember we talked about allocating flag objects. Okay, let's call it void alloc flag, and then so now iocto interret octo. Well, let's do it. FD is the command to allocate flag object. This is this thing. Okay, this thing. Okay, allocate flag, and then that's wrong. No, where does the command come from? uarg request. Oh, request is not checked, and wait. No, uarg is definitely need to be taken. So uarg is something that we don't know yet. So this is uarg. All right, let's check what is uarg. Uarg it's something. Uarg is equal to request to rec, which is this thing. Oof, what is this thing? Okay, let's see whether we have this inside. Oh, okay. Expand it. Okay, our beloved friend Ida knows how it works. So for k heap request, it has a ubuff and size. All right, let's define it in C. And size of 8 byte. All right. Struct. Okay, heap, red heap, and it has u. Yeah, it's 8 byte ubuff, and then u size. All right, and then type def. Unsigned long 64, which is 8 byte. And now we need to pass it to iocto. Okay, okay, heap rec t rec. Well, a good habit is to just do it like this. And you argue this request. Request. All right. So, well, when we write exploit, we also want to make sure things work as intended, or it will be really hard to debug. So usually I will check the return value. So what's the correct return value for iocto? Let's check. So this is 04. It will do this. It will return 0. If everything works correctly, it will return 0. So we'll assert it returns 0, and then we'll allocate flag. Let's allocate a ton of it. All right, let's see whether it works. VM connect, and then oh shoot, oof. Oh yeah, it takes the FD. And does it work? All right. I hate warnings. Well, let's see. C's iocto, I think. Yep. All right, and then VM debug. Notice that this is practice mode. So we have sudo. Oh, we're already in VM. So we need to sudo grep kheap iocto proc klc. Oh. Okay, it's here this time. Unrecognized. Are we in the VM? We are in the VM, right? VM debug. Oh, am I doing VM debug inside the VM? Oof. Is it? No, this is outside the VM, right? Practice kernel exploitation in level 1. Oh, I see why. Because VM restart. Because the last session got killed. The last session got killed by because of the SSH timeout. So it got killed. There is another session connected to the VM, so we need to restart it. All right. VM logs. Make sure. Well, it's booting. It takes really long time. It's okay. We're fine. Alright, SSG started. We should be able to connect it. No, so VM debug. Alright. So we're inside the VM. Kheap iocto proc kheap case OC. Notice that the function may be different across boots. Well, although it seems to be the same as the last time, but it may be different. So don't get surprised. Okay, so where is the allocation? Let's see. This is here, right? is the flag object is here, 113. Okay, 113. Wait, is it 113? All right, let's continue and then run the POC. All right, we hit next RDI. All right, RDI. Oh, RDI. This is actually not. Wait, RAX. Sorry. The return values are in RAX. All right. So should be the flag object. So after one more continued, it should contain the flag value. So let's see. So indeed, it contains the flag value. Why the first 8 byte is not there? Remember the data structure? It's a pointer and a buffer. The pointer is empty here. So if we do 8, we'll be able to see a progress flag. So yeah, we indeed have the flag inside the memory. We just need to read it. So now we need to find another way to exploit the out-of-bound read. So how do we do it? Let's continue. Control B, disable A. All right. Now we need to do read. Void do read. Int fd. So remember what we need. We need a buffer and a size. Void star buff size t size. And then we need to pass along a request. Request is ubuff is equal to buffer. This. And then size is equal to size. This should work, right? And then the read command is copy to user, this one, right? Let's see. Copy to user is we as user, we're reading from it. So yeah, this is supposed to give us, this is supposed to read from the object that is associated with the entry and then read out of bound outside of it, because like following the object, because the size is not it's not checked, so we can pass it. So what we want to do here is that we can open up a object, a k-heap entry. This will allocate a object associated as in k-heap open. Remember when we talked about k-heap open? This one will allocate an object, and then allocate a, like, let's say put a ton of flag strings into memory. Now we need to read from the object, read OB from the original object, the file object, let's say. And we should be able to read out the flag. But let's see. Do read. So we need to do read. Do read. FD. Oops, is it FD? Oh, it is FD. Buffer, let's say buff. Let's do this. And set buff, row size of buff, buff size of buff. So the thing I usually do is to create a function called hexprint that will print out the values in the buffer in hex form like this. Hexprint void buff size t size. Then for basically I want to print it like in GDB. I0 and this 0 2x I think, and then this should be okay. Then size buff plus I, let's do this. Let's do char. Well, void is better. And then char star. Plus I. Now let's hex print it. Hex print buff size of buff. I'm doing the office hour. Feel free to join. Okay. Alright. Needs a string header. Let's give it. I hate warnings. Oof, seems it's not great. Okay. Prints out. Let's do 8. Alright, we're seeing something that is very similar to char is not correct. It's unsigned char. Unsigned char. Unsigned. And that is too long. Let's bring 400. Alright, we're seeing things. This looks like a flag to me. Wait, chars can be assigned? By default, all chars are signed. So you have to say unsigned if you don't want to see weird output like this. So what is happening here is that it prints 0, it prints 7e, and then now it encounters f. Wait, is it f8? No, AF, and now it's a negative number, so it prints out 4 bytes instead of 1. So if you want to actually print it like AF instead of AF, you want to cast it to unsigned. See, now we're seeing stuff like just what we do in GDB. In GDB, do we have a like OX? We probably have OX, right? So we just want to print OX here, maybe. Printf OX and then OX, maybe just to make it look better, get a feel of GDB. Now, okay, we probably also want to print the size of it, right? So we know where it is. Print f the how long do we want it to be? 0, 16 x, and then like this, maybe buff. Buff plus I think. 64, cast it into that. Now we do it again. Now it looks like GDB. Oh hey. Yeah, we're learning how to hack computers. Now we can print this thing out, which is the offset is, this is 11, this is 9, so OX200. So we can print outputs. What is that? Oh, plus OX200. We're supposed to print. Yep. So we got the practice flag. That's how we get it. Let's just make things better. Now let's try it in real thing. And the good thing about pwn.college is that you don't have to. You can, after you debug, you can just wait. Yeah. After you debug, you just launch it into the real thing and it's supposed to work. Oof, flag. Yep, oh, yep. If you do your code right. VM logs. I think it is it. VM connect. And again, we're sorry about the slow machines. It's because of some technical issues. We have to disable the virtualization and also limit it into one core because our infra got hacked by Charcoal a few years ago. So sorry about that. VM connect. This is now no longer the practice, the VM. We got the flag. Yay! All right. Any questions? Actually, do you notice that in my POC, I assumed that I can just allocate an object, the file object here, and then put a ton of flag objects afterwards? This is assuming that flag objects will always allocate it after the file object, which is not true every time for Linux kernel. This is quite true for like because there is a mitigation called random free list. But yeah, this is some assumption here. We did here, I think for level 2, do we have this level 2? Yeah, in level 2 we are going to see it. It has this randomized free list, which means if you do allocate flags, it may not always land after the kheap open file object. Let's dive into it for a bit. So actually, the randomized free list It can be found in the source code. What source? Which version are we using? Correct. We are using 679. Okay, 679. Is randomized for list a config while compiling the kernel, or does Ubuntu have that by default? It is a, well, let's see it. It's actually a config, but then Ubuntu enables it by default as well. I think it's called free list random. Here. This is the configuration that is, it is configurable by. So yeah, this is one of the protection that is optional, but then almost optional. But then I think almost all the vendors have it enabled by default. So yeah, it's something you need to deal with in real world Linux kernel situation. Same with other stuff. But then we're in level 2. We're only going to focus on slab free list randomization here. So the way it works is quite simple. Instead of allocating objects linearly, when I say linearly, I mean this is object 1 and you allocate object 2. You have object 3. This is how you do in the level 1. But in level 2, there will be empty slot. Okay, like this. And then when you do the allocation, when the randomization is enabled, what it does is that it will allocate randomly for allocation 1, and then let's say allocation 2 here, and then allocation 3 here, which means the allocation is randomized. You just can't have a deterministic heap layout that you can expect. But is it true though? In fact, in our case, what you can do here is that you just assume that you can spray a ton of flat object. Let's say this is the file object, and then now the second allocation will be the flag. Oh shoot. Oh, and then this is the flag object. But what if you spray just a ton of flag object? It will be here, here, and then even more. Eventually, you will have some flag object right after the file object, and you can read out flag. Oh yeah, if we just fill up everything, we could still get flag, right? That is correct. Well, so the challenge, is there a max number of slots? That's a really good question. So for this information can be obtained by proc. I think the name of the cache is called kheap obj, and this information can be. Oh, we need to get to practice. Let's practice level 2. Yes, there is a max number of slots, and this information can be obtained through another proc entry. Let me show you. Git logs. All right, it's booting. Sorry about that. It's all Connor's fault. Definitely not mine. Connor refuses to compile our own QEMU, so we can give you guys more cores. Connor refuses to do that. So yeah, I don't know. Oh, nano. No, I'm not a nano person. Nope. All right. VM connect. Does kernel even use multiple core while booting? Yes. Yes. Dude, not SMAP. You mean SMAP? Yeah, that's right. All right. This information can be obtained from slab information. All right. Let me post it into the channel. This is important. Wait. What? Let's do this. Okay. This is not quite readable, but anyway, there is this magical entry that is only readable by root user. Wait, not really. Oh yeah. Oh, I'm here teaching you how to hack pwn.college, and if you just SSH into pwn.college, and you just cat proc slab info. Wait, what? No, it used to be readable. What's going on? It used to be readable. Oh, sudo. Exactly. See, if you are in practice mode, you can read out the secret information about how the pwn.college host machine works. Oops, Connor. Be careful. Somebody's going to hack your machine. Right. Never mind. So this secret information is supposed to be only readable by root. So in the VM, in the practice mode, you can read out the slab information, and we can see that the first entry is kheap object. So how do we parse this information? As well, it's not quite readable. Why is Docker now making our proc more hardened? What the fuck, Docker? Because you give students root privilege for practice mode. Dude, they are root. All right. So what it's showing here is that there are 0 objects inside the kheap object cache, and then like in total, sudo hack pwn.college, exactly. In total, there's 0 objects in it, and then each object is of size 212, and then the object per slab. Each slab contains at most 8 objects. So that answers your question that what's the maximum number of slots? That's 8 here. So, and then it says that pages per slab is 1. So that means that means one slab contain. Oh god, this is in the VM. We don't do it. That means there is one slab equal to contains 1 page. 1 page is OX 1000, and then we know that object size is what is it 512, and then so 512, that means we have 8 slots in the page or in the slab. We can do the same calculation for other random cache. Let's say this one. We don't know. I don't know what that is, but let's see. This means 0 means that there are 0 this kind of objects in memory. Each this kind of memory this kind of object contains. Let's copy that here as well. Contains object size. This is object size, and object per slab is 14. This is the number of objects that it contains in each slab. And then it says that this slab contains 4 pages. 4. So yeah. Do you understand the calculation here? basically, we can use this information to see how many pages are there in the slab, and then based on the object size, we can know the number of maximum objects in the slab. All right. If you have any questions, just ask. Interrupt me. It's totally okay. And then let's do some practice on level 2. And as I already explained before, if there is a magic flag object inside level 2, we can solve it with the level 1 with the level 1 script, because we can always what's it called? We can always spray a ton of the flag object and then use the outbound read to read out flag content, right? But then I'm Kyle, and I'm a bad person. In level 2, you don't have the magic. You don't have the magic flag object. Not related to current challenge, but what's k-malloc trace and k-malloc caches? How can we find what that is if k-malloc only give me an index? That's a great question that is not related to our current level, but sure. So that's, you're asking weird things, that in the sense that k-malloc caches is a variable. Oh shoot. It is a variable. K-malloc trace is a function. K-malloc trace, and it's used by ftrace, so it shouldn't contain much important information. Or it is the oh, never mind. It actually contains the what do you mean? What do you mean it's a function? As you can see in the symbol, it's a variable. But as you can see here, it is a variable, and you have an index. How do you your question is, how do you translate the index into the cache, right? It's actually, you can find it in the source code. I think it's somewhere here or here. See? No. Here. Oh, never mind. Oh, never mind. I think there's definitely a thing somewhere. I cannot find the translation, so we're going to do some dump way. Dump way. Oh god, it got stuck. K-malloc cache. So to other students, this thing is how k-malloc, when you do a k-malloc, how it translates a size into the cache. Oh, shoot. Okay. Let's do it like this. And let's do 2. And then, yeah. See? So basically, if I remember correctly, yeah. The first one determines the size, the second one determines the type. Oh, never mind. So what's going on? It used to be an array, so it's no longer an array nowadays? Alright, let's figure it out. Alright, yeah, as you can see, there's type, there's index. Create k-malloc crashes, or we can redo this. You can find it out in kmalloc. This underscore kmalloc here, I think. Node. This thing. Here. All right, let's continue with level 2. But feel free to interrupt me if you have any questions. Okay, so level 2. So yeah, the first thing we need to do is to college office hour. Okay, close this thing, don't save, and CP, challenge VMX, nope, challenge 2.ko, I think that's it. 64, challenge 2.ko. Alright, let's look at level 2. So for the kernel exploitation module, it was because it was originally intended for part of the quarterly quiz, so it actually doesn't follow the teach one thing at a time principle. So in this level, I think I introduced two new ideas in this level. The first is the free list randomization protection that is turned on for almost all the Linux distros. And the next thing is that there is no more flag object. Let's make sure of that. Let's dig in. So for the init, Connor, I think this is the old thing, but it works. Never mind. So it still creates a the cache and the proc entry. That means we can interact with it through /proc/kheap, and then exit. It doesn't matter. Going to open. So still need to. What's the size of this thing? Size is 1d8. Okay. And the first thing, first thing is a function pointer, and this is a buffer, and then moves it in here. This is Q2, it returns, that's okay. This thing returns an object t star thing, 2 pointer, and then pointer. Okay, let's look at iocto. This thing is the object. Let's call it file f object, and it's of the type object t, and then and spread out the logic. This is what I usually want to do. Reading user request, and then handle commands. From user, okay. So this is copy from user is OB right. OB right, because there's no check on the size as we talked about before. And then for this one, this is a function pointer, so So we have OOB write primitive. If we override the next object's pointer, a function pointer, that means we can have PC control. So this is actually granting us a control flow hijacking primitive. Cool. And then this thing is going to do copy to user. So copy to user takes three arguments, and there's no check on size as well. And this is OOB read. Alright, so there's no more flag objects, but the exploitation plan is actually quite clear. So we just need to allocate two objects, somehow make them adjacent to each other, and then overflow from the first object, override the second object's function pointer, and then invoke the function pointer in the second object. That's it. Sounds easy, right? Well, except that there is this free list randomization. So how do you make sure that you're overriding the right thing? So the answer is you don't. You just spray and just invoke everything afterwards. Or if you want to make things really clever, you can just be read, making sure that it's the correct function pointer you want to override, and then call all the things exactly. That's the answer. That's the spirit. Love it. All right, let's try. How do we do it? Let's try it out. Oof. There is no more a lock flag here, but then we have this. We have so this will allocate, and as we mentioned before, we want to make sure that there is one file object right after the first file object, so we can spray it. When we do spray, we can create a ton of FDs. Let's say FDs 10. Well, let's not do 10. Let's do 7, because we know that there are only 8 objects in one cache, right? So we can spray it 7 times. The first one is for the OOB thing, and then others are for sprays. For int I0 7 plus these high equal to this. Okay, cool. Now if we write out of bound into the OOB FD into this object, the vulnerable object, it should override one of the victim objects that we sprayed, right? And then so we need to override it. So we need to provide a do write function. Do write thing FD buff size. What is the do write thing? Copy from user is the do write. This is the command. And then the return value is 0. Okay. And then do write. Let's do write. OB FD. So there is one thing that is very tricky here in Linux kernel. Do you notice that in the cache creation, when we create a cache, we tell the cache, hey, we're going to create a size of at least 0.1d8. But the actual size is decided by the kernel what kind of size is going to give us. And the only way you can get it, you can see the real size that's used by the kernel is going to the slab info. And sudo grep k heap object, I think, like slab info. And then we see the size is OX200. Actually, OX200. So if we want to override the next object, we need exactly OX200. Why? Because we're overwriting. Well, we don't actually need to do 200. We can do 400. We overflow. We don't care. Then try buff a lot, and then mem set buff a size of buff, then buff size of buff. Now at this point we overflow because the size. Remember the size is OX200. But the buffer. But PTR takes OX8, so there is actually OX1F8 bytes before the next object. But anyway, we overflow everything, so we override into the next object's the function pointer. And if we do a call function, when we say call function, I mean do call. We need to have a do call communication with the kernel module, and then Y79, and then what does the call thing? What is the call thing? This will do the call, right? Call is this thing. All right. Call, that's call, but we definitely need to provide a valid. Well, there's no thing associated with it, so do call. And we do call is I. Looks correct to me. We're supposed to be able to crash the kernel here, but let's see. This is inside the VM. Okay. Okay, let's do pack. Oof, segmentation fault. What happened? VM logs. We actually just crashed the kernel because it tries to, and it's a RIP control. So what's the offset? As we mentioned before, there is OX1F8 bytes before the next object, and the first 8 bytes of the next object is the function pointer. So it actually controls the so we actually need to, well, I think it's 1F8, is it? Yeah, I think so. And then 4 star equal to, let's say, OX1. Dead beef. If our calculation is correct, this one should still crash the kernel, but at a with a PC control of that beef. Let's see. It's killed. What's going on? Well, we are at dead beef. Alright, so we have RAP control, but then in the past, I think in our previous kernel exploitation module, which we talked about, we can jump to user space and get shellcode execution and we'll root, right? Not so easy when we have the some protections enabled. Cat proc CPU ID. Where's CPU ID? CPU info, sorry. In the CPU info, we can see that there are, well, I'll probably send it in the chat. Proc CPU info. SMAP and SMAP. SMEP means that you cannot jump to user space. It will just immediately crash when you try to jump to user space. But when SMAP is enabled, that means you can still still use user space data. Like when you can do stuff like move RSP or like this gadget, and then you do a after this gadget, you return to it, and you do a mmap at this location, then the kernel will start dropping into user space. So it still works. But then when SMAP is enabled, this instruction is actually trying to directly read from user space, and it will crash immediately because of SMAP. What's the way learn from internet? Checking command line, but it didn't tell me the parameter you used. I mean, you can cat command line to see what we used. And SMAP and SMAP are enabled by default. So we don't need to specify the command line. So if send to KSR, if there is no KSR specified, KSR will be enabled. Is there no legit reason for the kernel to pass to user space, or there's some mechanism where it can? That's a great question. Remember, copy from user and copy to users. Only during those function calls, it will enable a special instruction that will enable access to user space. So it can directly access user space, but then it will immediately turn it off after the communication with user space. We can check the source code. I think it's like this: copy from user, maybe. Is it KPTI enabled by default? You can check. I don't know. Grab PTI. We don't have it enabled, but don't ask me whether it's. I think it's enabled by default. But yeah, I can check my computer. Oh, let's check. Why check my computer when we can check pwn.college's computer? Grab PDI, CPU info. Well, apparently, wait, yes, it does have it. All right. How do I? PTI. So yeah, apparently pwn.college have PTI enabled, which is good. And then pwn.college also has SMAP enabled, but pwn.college doesn't have SMAP enabled. So hackers, you know what to do. Just exploit pwn.college infrastructure and get all the flags. And you can check how pwn.college enables the kernel. As you can see here, pwn.college's kernel is 540.173, and then enables. There is nothing in the argument, which means it will enable all the protections that it can. So yeah, that answers your question. PTI is enabled by default. Cool. And then let's see, what were we talking about? We were talking about. Oh, we were talking about what to do with the PC control, right? So when we were talking about kernel. Okay, that's correct. We're talking about kernel ROP. So now we have PC control. So the first thing we actually need to do is to see, besides the kernel control, besides the PC control, what else do we control? That's very important. We should VM restart at this point. But yeah, as you can see here in the assembly, we can see besides the PC control, we also the buffer content will be passed to the register. So that means we at least have PC control and the content of RDI control. I think Jan told me that he taught you guys how to use run command, the run command thing in the Linux kernel to exploit for the exploitation. But then that thing no longer works in the latest kernel because run command is no longer it's inline. It's no longer a function. As we can see, maybe. What's going on? Oh, dude. But VM restart. Can't believe I'm doing VM restart inside the VM. But anyway, what? It's in line? Yeah, it's in line. Yeah, it's no longer. Let's see whether let's in pwn.college. You know, in pwn.college thing. Let's do sudo grep run command proc klsim. It's okay, Connor. Proc klsim is filtered by Docker. Oh shoot! In pwn.college's kernel, run command is still a thing. Oh my god, Connor, this is terrible. VM connect. That is correct. You're right. The command will be copy pasted everywhere inside the kernel. That's correct. VM logs. Oh god, it's taking some time. But dude, just look at my kernel. My kernel is not quite new. It's only 6.5. It's not super new. Grep run command. Run command. Probably not. Don't do sudo. Proc klsim. God damn it! What's going on? Apparently my kernel has it as well. All right. Well, do we still have it inside? Inside this thing? Grep run command proc klsim. See, there is no such thing. There is no run command in our target VM. Almost. Well, so in our build, at least in our challenges, there's no run command. So what can we do with a RDI control and a RIP control? There are actually many more methods. One way is to actually just do. Oh, by the way, about so we definitely need some good gadgets here. So I would recommend everybody using Zoluto's thing. Work on. Oh my god, let's enlarge it. CP challenge VM Linux here. Zoluto has this K wrapper. That is super good for kernel exploitation. I would recommend everybody to use it to find gadgets inside Linux kernel. All right, let's use it. K-wrapper and then VM Linux gadgets. You'll find all the gadgets inside the Linux kernel within seconds. The only complaint that I have about K-wrapper is that the output is not sorted. It's terrible, apparently, but it's okay. Rep, move R. What do we want to do? Move RSP, RDI, gadget. Let's see. Well, there's no magic gadgets here now. So what do we do? Panicking. So what we have here is now is a RDI control and a RIP control and the control flow hijacking primitive. So we can transfer it to something even more powerful. No. Let me check. It's still in the run command thing, if I remember correctly. And then it's work. Well, apparently, I forget what it is. One sec. Work for CPU. Work for CPU. Fuck. This function has a really good primitive. As you can see here, if you control the content of RDI, you can actually control the RDI entirely, and also the function pointer. You get the function pointer as well. So and then you can commit creds, init cred. That'll be it. And that's how you privilege escalate your privilege. So did Connor talk about how init cred works? Basically, when Linux kernel boots, it will launch only one process, which is the /init process, and only one user, which is root. And root user's cred is the init cred. And you can see here. P-init cred. As you can see, it belongs to the root user. This is init cred, by the way. Init cred has a usage count of 4, UID 0, GID 0, SUID, blah, 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 everything 0. And then it's just some functions associated with it. Doesn't matter. Which means if you commit creds of init cred, your process will be going to have the root user's cred, and your root. That's what you can find on the internet about how this exploitation works. But remember, initially we need to transfer our control into work for what is it? So this is just an ID card that says your root? Exactly. So we are borrowing root user's ID card saying, I'm root. So yeah, I think you probably should have seen this payload, prepare cred, now commit creds. Everybody have seen this before, right? Prepare cred, now commit creds in the past, right? what prepare commit, prepare create null in the past is literally returns init create. In the past, it's no longer the case these days. Let's see. We probably do 5.4, like what pwn.college is using. 5.4. Yeah, prepare create. Oh yeah, prepare create. Wait. Prepare. Is it prepare create? No. Commit create. Wait. That doesn't make sense. I'm confused. Prepare create. Or prepare create. No, that's wrong. Prepare kernel create. What am I talking about? Prepare kernel create. Sorry about that. Yeah, that's prepare kernel create. This is the old. This is the old code from pwn.college's kernel. As you can see, when you do prepare kernel create null, which says daemon is equals to null, you will go to this branch, which literally says, give me a copy of the init create. So which means when you do blah 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 kernel create, what you are doing is literally commit create init create. So why not just do it directly? Exactly. You just grab init create directly. So we also looked at the init create content in past, right? It's actually not hard to fake. What if we just fake init create and then fake init create in our in our fake object, and then we commit it? So how do you get init create these days? Or it's actually very difficult now. It's quite simple. It's inside the kernel data section. It's not randomized. You just use its address. That's it. Great. So that's one way of doing it. Another way is you just directly fake this thing. Put all the data. It's 4000 blah 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 some things. Put it into your buffer, and then call your PDI control. And then invoke your the PC control and RDI control, and now this RDI points to your faked create, and then you become root. That's actually how I do it, and I don't think you can find it anywhere on the internet. But then that's how I do it. And we're already at 6. So I guess I would just end the office hour now, and I don't think I have time to demonstrate how it works. But yes, that is intended, and I do have a POC here. But yeah, let me write down what we talked about in the chat so that people can the important work for CPU FN. That function is important. And init create. Where can people see more of my kernel shenanigans? You can check out my blog. Apparently it's down for whatever reason is that. Well, nobody's attacking me, right? Let's reboot the server. But yeah, you can find all my more of my thing in cowbot.net, and then I will probably do some more office hour in the future, if Connors want me to be here, and yeah, that would be it. Should have got a server. Alright, that's true. Alright, see you guys. It was nice talking to you guys all. See you next time.